In the modern world, our reliance on complex, interconnected systems is absolute. We depend on electrical grids to power our homes and businesses, communication networks to connect us globally, transportation arteries to move goods and people. Trillions of dollars are invested annually to build, maintain, and upgrade this critical infrastructure. Advanced monitoring technologies, sophisticated engineering practices, dedicated teams of professionals work around the clock. The explicit goal is near-perfect reliability, a seamless background hum that supports daily life and commerce. The expectation is that catastrophic failures should be exceedingly rare, yet large-scale system failures continue to occur with startling regularity. A major airline's computer system can ground thousands of flights, a regional power grid can collapse under a heat wave, a critical financial clearinghouse can freeze transactions worth billions. These are recurring patterns. The more we invest in infallibility, the more spectacularly systems can fail. This raises a question beyond technical faults or human error. Why do meticulously designed, heavily funded systems still break down? After downtime events, reports cite causes like a faulty software update, aging hardware, or an unforeseen external event. Those explanations are correct but incomplete. They describe the what but rarely delve into the deeper why. They miss systemic pressures and hidden incentives that let vulnerabilities persist year after year. The true story isn't just broken parts or coding mistakes, it's a complex narrative of economic incentives, organizational behaviors, and trade-offs between short-term costs and long-term resilience. Understanding stalling systems means examining decisions, policies, and financial pressures. It's about the hidden architecture of systems, architectures that can favor efficiency over robustness and create failure conditions. The cost of downtime is lost revenue, inconvenience, and erosion of public trust. Let's take a look at the complete system overview. Critical infrastructure networks are not monolithic entities, but complex ecosystems. At the core are owners who set strategy, operators who manage daily operations, and regulators who enforce safety and service standards. Two currents keep this system alive: data and funding. Data flows up from assets to operators for real-time control, and then to owners and regulators for oversight. Funding flows down from users, paying for everything from maintenance to major upgrades. This creates a constant trade-off. Deferring maintenance can boost short-term profits, but it introduces hidden risks that can lead to major failures. When a failure occurs, accountability often becomes diffused. This structure can create gaps where no single entity has total responsibility, setting the stage for recurring problems. When a critical system fails, the first explanations point to tangible surface causes. We blame aging infrastructure, a corroded pipe, or a worn-out switch. We point to extreme weather, a hurricane that overwhelms our defenses, or we cite digital failures, a cyber attack or a software glitch that brings everything to a halt. Even human error is a common, relatable explanation. These are the straightforward, visible causes of downtime. But this narrative is often incomplete. It explains the causes, but not the systemic failures. The critical question is why a component known to be aging was not replaced proactively. Why was the system so fragile in the first place? Why were cyber defenses insufficient, or flawed software deployed? These surface causes are the final, visible links in a longer chain of causation, forged by deeper incentives, financial pressures, and management choices that allowed the risk to grow unchecked. Section 1. The incentive to build, not to maintain. Beneath the surface causes of aging assets and underfunding lies a more fundamental driver, a systemic incentive structure that overwhelmingly favors building new things over maintaining existing ones. For public officials and corporate leaders alike, new infrastructure projects are highly visible and politically rewarding. A groundbreaking ceremony for a new bridge, a high-speed rail line, or a state-of-the-art fiber optic network generates positive media coverage and creates a tangible legacy. These projects are associated with progress, innovation, and economic growth. They create construction jobs. They provide clear, photogenic evidence that leaders are taking action and investing in the future. which can be a powerful tool in election cycles or quarterly shareholder reports. In stark contrast, the work of maintenance is almost entirely invisible. There are no ribbon-cutting ceremonies for replacing a 50-year-old water main or upgrading the software on a power grid's control system. This work is slow, unglamorous, and often disruptive to the public in the short term. Its primary benefit is the prevention of a failure that might or might not have happened in the future. Because successful maintenance results in a non-event, the continued, uninterrupted functioning of the system, it is incredibly difficult to celebrate or use for political gain. The funding allocated to these crucial tasks is often seen as a pure cost, a drain on the budget that produces no new capacity or visible improvement. This disparity creates a powerful feedback loop. Political and corporate capital is rewarded for initiating new projects, which in turn encourages the allocation of discretionary funding and top talent towards these high-profile endeavors. Meanwhile, maintenance budgets are often the first to be trimmed during periods of financial constraint. The organizational departments responsible for asset management and routine upkeep can become backwaters, struggling to get the resources and attention they need. Over time, the system's capital assets expand, but the resources dedicated to sustaining those assets do not keep pace, leading to a gradual but certain increase in the overall fragility of the network. The result is a system that is perpetually growing older and more vulnerable, even as it expands. The very incentives that drive its growth also sow the seeds of its future failure. A new highway extension is built, but the funds to properly inspect the bridges on the older parts of the same highway are reduced. A company launches a new digital service, but neglects to patch the legacy servers that the new service relies upon. The cycle of building new infrastructure while under-resourcing the old is not an accident or an oversight. It is a rational response to a system that rewards visibility over stability and tangible construction over the invisible work of prevention. So, that is the perverse logic at work. Beyond surface causes, hidden drivers systematically increase fragility. The decision to defer maintenance, for example, is often a calculated economic choice. From a short-term view, delaying a large replacement seems like efficient capital use, but this creates a hidden maintenance debt, making the system fragile until a minor shock triggers a cascading failure. This is compounded by a mismatch in time. The slow, deliberate pace of regulatory approval for funding clashes with the rapid, real-time decay of physical assets. This can create a perverse incentive to wait for something to break before asking for the money to fix it. Finally, technology itself can be a trap. Over decades, systems become a complex patchwork of old and new technologies. This technological lock-in creates inherent fragility, where the primary goal shifts from optimizing performance to simply keeping the disparate parts working together. These hidden forces create a permanent state of elevated risk, independent of daily operational choices. The story of infrastructure downtime is a story of systems working as designed, even if the outcomes are unwanted. Recurring failures are not random accidents, they are the predictable result of a core, unresolved tension, the trade-off between short-term efficiency and long-term resilience. A system optimized for maximum efficiency operates with minimal redundancy and lean inventories. This drive for efficiency keeps costs low for consumers and maximizes returns for investors. Conversely, a system designed for resilience features redundant components and extensive preventative maintenance. It is far more robust but also significantly more expensive to build and operate. This creates an inherent conflict. How much are we willing to pay today for a problem that may not happen tomorrow? This is not a simple technical question. It is a question of societal values. As risks from extreme weather and cyber threats grow, the cost of failure continues to rise. How we choose to strike this balance will ultimately determine the reliability of the systems we depend on, and the true price we pay for their inevitable stalls. You've been watching System Atlas exploring how the world's systems really work. Share your comments below. See you in our next episode.